Historically, people have dealt with the symptoms. They see something falling down on the inside of a wall, they stick it back together, sometimes they repair the outside of the walls. But when you've got such a difficult building which has been developed over so long with different elements fitted on at different times, what you tend to find is that the problems are less obvious to cure than you would otherwise think. We have a look at the overall building. You start with the low-tech side, you start with the simple, obvious thing. You look at how the gutters work, how the roofs work, how the walls work. Is it failing? Because a lot of this stuff is really obvious. And then you tick off all of those, you get rid of all the simple ones and see what you're left with. Often you're left with areas of damage which you really can't answer like that. So one of the things we do is called core sampling, liquid moisture sampling, to see if water is actually going through the wall. What we do is, having identified a risk area, we drill a very thin core into the wall and then actually look at the moisture and salt in that core, and you can tell if it's coming from the outside, if it's condensation from the inside, and using that you can often tick off the next level of problems. And you go through in this iterative approach, breaking it down piece by piece. We use lots of tools. There's a lot of thermal imaging going on at the moment because one of the nice things about water is as it evaporates it uses energy and then it cools the wall down. And so without touching, without making holes, you can see a pattern emerging which then ties into the damage pattern. You can tell that's somewhere you've got to investigate.
So we're clearing out the cement from the joints, and then we're packing all those voids, hollows and interstices with lime mortar, with hair through it, and modern thermal blocks. And those thermal blocks are made with volcanic ash from Iceland. So they're entirely permeable, they sit really well with the whole idea of reversibility, and they're also clearly identifiable as a material introduced in the 21st century. And they're rammed, wedged, pinned and driven into the core of the wall, and then we use smaller pieces to bring the wall face out flush. Once that's done, we then have to produce a finish which sits comfortably with that whole Lutyens aesthetic. And we're doing that by applying the finish point, sneckhal, sneck point, whichever you want to call it, onto the wall. And while that material is still wet, we throw a mixture of sand and grit at the wall. So that's what we're doing in this second phase of the trials of Lindisfarne.
We've set up a glazing program over 3 windows with a specific specification to prevent water ingress both through the panel and around its perimeter edge. Part of the specification, or the brief as it were, was to retain as much original material as possible. So we've retained, as you can see here, all the original lead and all the glass. The big difference between what existed before and what has happened now is that we've changed the fixing detail within the stonework, where the leaded panel fits into the rebate of the stonework. Part of the problem has been when wind hits this building, it doesn't blow the windows into the building, it actually sucks the windows out. So what we've done, we've created a groove within the glazing rebate. So it's impossible for the windows to be sucked out. And all of that internal fixing has now been covered with sand mastic pointing. So from the outside, you can't see the structural fixings within. From our perspective, our long-term aim is that by the end of the test bed in a year's time, these windows still don't leak, and that would be a tremendous success for us.
What it basically comes down to is, at the end of this, will we in our minds have a full picture of where all these damage problems are coming from and how we can control them? And if we can, then we can repair the building in such a way that it'll survive.